Next up, we have Michael Bentley talking about detecting malware. I asked him over lunch, of course, getting barbecue sauce everywhere, having a fun conversation, how I should introduce him, and he was like, oh, no, I don't really do anything. You don't do anything? He's like, oh, no, I'm going to Vietnam for a few months, so you should follow up questions with him about his future vacation plans. So everyone welcome Michael.
Well, thank you very much. So my talk's about malware tracking at scale, which is actually kind of a big problem for us. When I was at Lookout, we would get in about 100,000 applications a day that were unique by at least SHA-1. Maybe the internals weren't so different, but it's a lot of applications to go through and analyze, and it's a problem that's kind of plagued the industry for a long time to solve, where you don't want to throw people at it. So about me, Michael Bentley, I was the Director of Research and Response at Lookout, currently working on some data mining projects, or as a friend put it, so you're working, you're just not getting paid. Fun employed. I don't have a Twitter account. I did have plenty of them, but my bots that I run on Twitter are working perfectly, and my Twitter account that has no bot, which is my actual one, got flagged for bot usage. So there's a learning model for you. If you want to find me wherever I am, sometimes my amateur radio call sign's the best. I do publish my location via APRS, which is kind of fun. And I'm still okay with receiving emails, so feel free to send me one if you have any questions. So what we're going to go over is, what are we trying to accomplish? How basic heuristics work. I need to give just a real brief primer on how we detect malware. Where basic heuristics don't work at all. How we can track malware with pairwise similarity and using things like MapReduce to kind of ease the burden on our researchers, and some visualizations that will help us extract more information from that. And then I'll go over some of the mistakes and caveats that we ran into while learning how to do this at a much larger scale. Let's see here. So what are we trying to accomplish? We're searching for major versions of software. So you have 1.0 is a major release. You got your 2.0. It's a major release. Malware is really no different in that. Often we actually find that the groups writing malware often have bigger engineering teams than you do. Sometimes it's dozens of people or even hundreds. These are people that are well-funded. They have good reasons to be writing it, which is money. Finding ways to detect it with simple heuristics. You can have the coolest backend in the world and all kinds of amazing things that you can do, but it's not going to run on someone's phone, or it's not going to run on their PC or on some IDS. We have to find a way to track the malware. Detecting something and tracking it is different. And then how can we use that to have better data set discovery for what we have? I'd like to think that if you have 100,000 applications coming in a day, and you're pulling that data out and you're extracting it, you should have a wealth of information stored somewhere. But if you don't know what to search for, it's really not going to provide you any value. So simple heuristics, that's detecting on static data. That's data that exists in an application. I'll kind of orient towards Android for this because it's a little bit easier for me to talk about. When you think of what's in an Android APK, it's really just a zip file. There's a Dalvik executable in there. There's a bunch of resources, like icons and things like that. So you can look for what's already there. And then your analysis stack may also create metadata about it. So you have all these applications. Maybe they're in the Play Store. Maybe they're in the iOS, the App Store. Maybe you're downloading it from Aptoid. We can acquire binaries from phones as well, but no user data. And so you have all these applications, and you have to acquire them. So we have crawlers that are running, pulling all these things down and downloading them. They come into an analysis stack, and then there's some data that's output. So we got hashes just like everybody else. So a hash is going to be, we're going to extract out the icons from that zip file. We're going to get a hash for all of them. There's strings. So when you go through the resources that are associated with that application, or you go through that Dalvik binary, we can get strings on things like URLs. So if you were to take apart Lookout's mobile app, somewhere in there's going to be a URL where that application is checking in. We were talking about Instacart earlier. Somewhere in their application, it says where to phone home. Things like class paths are going to be in there. Sometimes really, really funny comments from developers are in there, actually make good heuristics. And then the other thing that you're going to get out that's pretty basic is who signed it. If you're thinking about mobile apps, somebody has to sign it with a certificate, saying, I'm this person. You can make up whatever's in there, but you still have to sign it to get it into the store. So on those hashes, that you can get a hash on really just about anything as long as you can afford the resources on the phone or on your back end to kind of expand everything out and crawl it. So you'll have a hash on an APK or an IPA. You're going to have a hash on things like icons that exist in there, maybe hashes on the DEX file. And that's something it's super simple to write coverage on. String detection, so if you were to just open up that Dalvik executable in a hex editor, in this case you see, it says ru.esperbankmobile. Something, I can't read it from here. That's one that I downloaded from Contagio a few days ago, which is a really good source of malware if you're interested in this, that's freely available. What you can do is you can write a heuristic on a string that's delimited by null bytes. The reason why you want to delimit it by null bytes, that 00, is you want to make sure that you're not wild carding out in both directions, because if you think that you have something that's unique, it's probably not, and you're going to false positive, and then you're going to be telling people that something's bad when it's not. Malicious class paths are great to write coverage on, as long as you can do it. So you may have an application, maybe it's Pokemon Go, that seems to be popular, and then somebody repackages it. The game still needs to work, but the malicious part they added, that's where you want to write the coverage for that client detection, so that you're only detecting the malicious one and not the one that's not bad. Bytecode. And then, it's an exact match. So effectively, when you have malware detection, or it doesn't have to be malware, but for malware, you're kind of running Control F on the application. There's some art to how you normalize that data and how you present it to the engine, but it's Control F in the end. And then on certificates, the third one that we can, write coverage on and inspect. Certificates, if I'm Lookout or Instacart, which we had, earlier, they have to sign their application. It says, here's who I am. The contents of that certificate is the X509 data. Nobody's there actually telling you what to put in there. I can put in, a certificate and say, I'm Instacart, or I'm Lookout, or I'm anyone. The hash won't match, but the contents I can tell it to be really whatever I want. You can write coverage on that, but it can also be, a little bit problematic because there's no authority around it. There's nobody that's actually controlling the certificates, so I can make 1 million certificates a day. If I want to release a whole bunch of malware, I'll release a whole bunch of certificates so that I break your coverage. In this case, I pulled down some malware from Contagio to inspect, and this same malware, it's written by a group probably out of Russia, but in this case, if you look, it's the same malware, but it's just been re-signed, so this is the X509 content. So where that works well is for things that don't change. Heuristics work great for things that don't change at all. It's not really different if you're talking about an IDS. It's not different if you're talking about malware detection. It's all about the same, and it's computationally cheap. So if you have, say, something that's not being iterated on, just write some heuristics and you're going to be good. Don't worry about it. Call it a day. Where it's problematic, anything with funding or making money. So the malware that's coming out of, say, like Eastern Europe, most of the malware I see, if they have a major version, they may repackage that same application and make 10,000 APKs that do the same thing so that they can break all of your hashes. They're re-signing it so that your certificate detection isn't going to work. Everything that's coming out of kind of a more Asia region, especially in China, they're packing everything, they're obfuscating all their class paths. The same thing that you're doing to protect your legitimate applications so that people aren't reversing it, malware writers are doing as well so that your heuristics won't work. And then there's groups like Hacking Team. I don't know if you remember last June, they're a group out of Italy that sells software to governments to put on citizens' phones so that they can surreptitiously track you and find out where you're going without you knowing about it. Hacking Team got owned into oblivion, and it was pretty interesting because all of their Jira got leaked, all of their Confluence got leaked, and we were able to go through and find out where this company in Italy was actually taking the Lookout app and making sure that they were iterating enough to where that the coverage was missing so that they could sell their application for just a ton of money to governments. And then another interesting one is code taken from Stack Overflow. The way that you send an SMS to send an alert to somebody to say, hey, your order's ready, or your driver is here to pick you up, is also the same way that you would send an SMS if you want to do like MTAN theft for like bank fraud or something like that. So you're making the same API calls, and there's quite a few cases where people are copying code from Stack Overflow that is either good code. Sometimes it's a little hilarious, like people actually copy encryption keys, and you're thinking, cool, I'm gonna write coverage on their encryption key. There's no way that this is gonna false positive, and then you find out they copied their encryption key from Stack Overflow. That's super hilarious, but annoying. And then hunting for major versions. So let's say I wrote coverage on a application that is exfiltrating your data over SMS. But in the next major version, they switch over to exfiltrating your data over email or HTTP, and they deprecate that code. All my coverage just disappeared overnight. So I went from having detection, but I couldn't actually track it. What we did to start trying to solve this, I will warn you, I'm going to show you a CSV, which is probably like the most basic thing that y'all are going to see today, but it actually works really well for us, is pairwise similarity of applications. This is actually where it became a good solution for us. So earlier I said we had hashes of applications. So in this case, if you're looking under the column that says file hash, that's an application of a hash of an APK. The nearest neighbor hash is a comparison of, okay, how close is this to me? So if I wanted to say I was going to compute pairwise similarity of everything in here, I'd say, how similar am I to you? How similar am I to you? And so on and so forth through the whole crowd. And then the next step would be I would start with you, and then I'd compare you to every single person in the crowd. So it turns into a big exponential problem that you have. But what we're able to do is we're able to say, okay, everything in cluster 0, we don't know what it's related to. We don't have enough data. Everything in cluster 1 is at least 85% related to each other. So the one that's in white that says 5B, 6D, if we compare that to the APK to the right, it's a 100% match. It has a different hash, and if you're interested in how that works, I can go into that if there's question time. But we're able to say that these are effectively the same application, even though they have a different hash. If you look at the next one where it says BBA, that one's 98% the same. So what if that 2% was where they actually switched how they were exfiltrating your data? Historically, your heuristics would have disappeared, but now we can say, you're still the same thing. Walk like a duck, talk like a duck is probably still a duck. The problem that it helps us solve is, earlier I said you're doing Control F. Imagine if I came to you and I said, okay, I want you to write a search engine for Wikipedia. So what I want you to do is I want you to go to the first page in Wikipedia. I want you to find a unique word, and then I want you to scan every other Wikipedia document and see if it detects. And then when you're done classifying that one, you move on to the next document. It's the same thing with applications. We want to solve that. We want to make sure that we don't have researchers who are taking an application, which is in this case represented by these gray dots. We don't want people starting with one app, rescanning the whole corpus, finding out, did they match, did they false positive, moving on to the next one, rinse, repeat, ad infinitum. It's a terrible problem to have to deal with. And how people typically deal with it in the industry is they throw people at it. They'll have 200 researchers at their company when they're just writing heuristics all day long. And it's not fun. And everybody knows we want to have fun. So if we do pairwise similarity, what we can quickly find is, in this case, it's the same dots, it's the same graph, but purple, for example, starts to stand out. That's a cluster of applications where we can say everything that's purple is 85% related to everything else that's purple. Everything that's black is 85% related to it. So kind of a more straightforward one, it ends up looking like this. So you'll have these 3 APKs where cluster 1, all 85% similar, but the nearest neighbor for one APK may actually be in another neighborhood. So we can actually start to take what was traditionally something we couldn't treat as a neighborhood, and we can start putting it into nodes and edges. So in this case, all APKs are both nodes and edges, and the neighborhoods that you're seeing are effectively major versions of malware. And like I said earlier, the one on cluster 0, that means we didn't have enough data to actually classify it. If we actually break that out, it ends up looking like this, to where I can say, okay, purple, and I kind of wish we named malware variants by their color. That would be so much more interesting than .A. But purple is, that's a big cluster of malware. I can tell a researcher or ask a researcher, hey, work on this one. I've already pre-clustered everything for you. We don't need to go through and rescan the whole corpus. On the green one, if you look, where it goes into that nice teal or whatever color that is, that's where they actually iterated, and they changed some functionality where it would have broken traditional heuristics, but we can actually start to track malware authors over time and what they're doing and work a whole lot smarter on what we have. If we compare this exact same graph versus traditional heuristics, button. I can write this, but I can't work a button. Can we push it forward? Oh, I'm sorry, can we go back one? I apologize. Is it possible to move back a slide to 17? All right, let's see if it works this time, if I don't mess it up. So if we compare it versus traditional heuristics, so you have the same graph of this malware family where the colors are all the same, but where you see the orange, that's traditional heuristics. And if you look at that, you can start to tell that here where it's orange, I wrote coverage on these certificates, who signed it, but you can't really divine any or derive any intelligence from that. It's just a heuristic, but it's kind of a smorgasbord. You don't really know what's going on. So if when you start with heuristics, it's not helpful. If you start with clustering, then you can start to actually get a ton of intelligence about applications. So if you notice where the orange comes out to the gray area, I said everything that was gray earlier, we didn't have enough data on to actually cluster it. What I can tell from this right here, though, is I can say, okay, we have an acquisition problem. We're missing some of the data to where these should have been clustered together, so maybe we're missing a minor version of malware. So we can actually start to say, here's all our clusters. Let's extract all the metadata out of these applications, and then let's crawl the rest of the corpus and see what comes out. Unless you've been owned into oblivion, nobody's going to have a copy of your signer, even if it's malicious, even if you're making multiple copies of it. And we can use that to actually crawl the data set that we have, which is huge. I think it's 30 million applications, and start to find, okay, where do we have problems? Where can we write coverage? And it just helps us a ton. Earlier, there was a really good talk, and it was talking about how it's useful to look at things over a time series. So you're looking at multiple versions of a single piece of malware that we actually ingested over a period of about 14 months. So if we were to actually take this same data and then we put it on a time slice where we're sliding on a 4-month window, we can actually start to show and prove that the malware writers are actually iterating the same as we are on our coverage. What that ends up looking like is this. So when it first started, we only had a few applications. The first variant that they came out with is represented by the black cluster. And what will happen is we'll write coverage. We'll start to actually track the one variant that's black. And as we write that coverage, they'll start iterating and trying to break our coverage of it. And they'll come out with a new variant that happens to be pink in this case. So in the center of this is the current point in time. And as it moves out, it's over that 4-month sliding scale. So we can actually see that it's like radar detectors of the cops. It's just, there's no winners. It's just back and forth. Who's writing coverage? Who can do it better? And over time, I have this belief that you don't really, most of the time you don't defeat malware writers or authors. Every now and then they will switch to an entirely new family. They'll switch to an entirely new application, but it's pretty rare that you actually get the people to stop doing it. So if you see a variant, so let's say the pink variant were to disappear, that doesn't actually mean that we won. That may mean that we actually have a problem with our acquisition or we're missing it. So it's important to actually be able to view this over time and to see, okay, where did they go? And this thing will just wrap up here in just a second. I think it's about 2 minutes long. All right. So problems with doing pairwise similarity of applications, we get 100,000 applications a day. If you have 3,500 applications that you want to compare against 3,500, these are applications that we don't actually have source code on. These are people where it's an adversarial relationship. So We have to take all these applications, we have to use a decompiler, we have to get it into, in the case of Android, you'll get it into, you know, kind of a Java code or something similar. And it ends up being 12 million operations just to do all those comparisons. If you want to bring in more applications, you're either going to have to scale your MapReduce cluster by quite a bit, or find a way to reduce, you know, in how much you're actually bringing in. For example, to compare 3,500 applications, we do it in Amazon, but if you want to use MapReduce on it, I think with 128, it's either large or extra large instances, it still takes about 8 hours to run and compare all this data. It's just not possible to do unless you're using something like that. Interesting things, you can overmatch on similarity depending on how you calculate how similar apps are. So for example, if I'm an application and I compare myself to you, but you have an extra class, I have 100% of the code that you have, but maybe you're not 100% related to me. So that's an interesting thing that can come out of it. So overmatching. Doesn't really cause a problem. It actually gives a little bit of a benefit, and that's how we can use it to map out the neighborhoods. Tripping over the bar, which I have done actually an exceptional amount of. Pairwise similarity for 7,000 apps is about a 5 gig CSV of just text. So is S3. So when we first piloted this, we've always had the ability to do similarity of applications, but doing it at a large scale. You know, first you write it on your laptop, then you move some of it into whatever service you're using, and you start running into those, you know, interesting intermediary issues. But we ended up having issues where the data was too big for S3, and I ended up spending 3 or 4 days just troubleshooting CSV sizes, which was frustrating, but funny in hindsight. It doesn't work well in small applications. So if you think, okay, I just have a really, really tiny application, well, it's going to have maybe the Android support library in there. That can throw off your matching because every single application is technically related a little bit because you all have the same support libraries, basically. So small applications can be problematic. There was a little issue where we made a mistake, and you know, I was leaving 70 gig temporary files on the local machine and not cleaning them up, and it would cause just intermittent issues. That was kind of fun. Some knowledge on this. So I went to Lookout, I guess, about 2.5, 3 years ago. I had no formal education in graph theory. My background's in forensics and security. We use NetworkX, you know, to do this. So I had to learn how to use NetworkX, but it's actually very well documented and helped at least with the graphing and showing that we could treat things as a network. I didn't even know what GraphML format was, you know, 2-3 years ago. The thing that kind of got me started on it is I saw a PyCon talk with Gilad, and he was talking about how to do this with Twitter data, and it all works the same. It seems like it works very well for anything where there's, you know, interconnected people or applications. So he had not put up his source code because what everybody says is like, I got a talk, and I'm going to put my source code up after the talk, and then maybe they don't. And so I ended up like zooming in on his YouTube videos and trying to figure out what the hell is he actually writing. So that was actually a huge help. Gephi was a great shortcut for visualizing in 2D until I learned how to, you know, use things like D3 a little bit better. My team at Lookout is just absolutely amazing. Seth Hardy is this brilliant researcher, and he helped ask, you know, or answer all my like insane questions about graph theory while I'm trying to read Wikipedia and learn what the hell I'm doing. So he was just a huge help there. Jack Urban, who's a researcher also at Lookout, was the first person that proved that, hey, if we you know, start clustering things by time series, then we can actually plot this out over our entire data set. And if it's something that you want to get started in, like, okay, how can I compare applications so that I can start doing pairwise similarity? There's a great library in Python called GenSim with just awesome tutorials where you can start doing, you know, similarity of things. You'll have to figure out how you want to get the data out of the application. You know, you can't just throw an APK into GenSim, but you can extract that data. I'm happy to kind of give some basics on it, you know, afterwards if anybody's interested. And this talk was actually mostly inspired by a DEF CON 22 talk by OpenDNS, which is actually far better. But they're doing the same thing, basically, in tracking malware at the network and ASN level and proving how basically you can all just treat it as a network and, you know, how it's all related. That's it. Are there any questions? We got 1 minute. Yes, sir?
Hey, sorry about that. I'm just a random person who's not wearing a hat, so I thought I'd ask a question.
You're supposed to be under the floorboards this time?
Someone was paying attention to my earlier questions. So one of my favorite papers about real-world machine learning ever is Outside the Closed World by Robin Summer. I don't know if you've read it by any chance.
I haven't, but it sounds like I should if you're talking about it.
You really should, because like one of the most popular things for like a random PhD student in machine learning to do is some kind of network intrusion detection or malware sort of clustering model or whatever. And these guys basically wrote this paper that they just like, slam dunk all these clowns who think they can just do machine learning without knowing anything about security or malware or anything like that. Just sort of basically coming from this perspective of ignorance about the domain and just building models and stuff like that to solve these problems. And so I guess what I'm wondering is, with all the deep learning stuff that the cool kids are doing these days, have you seen any like actually useful applications of feature ignorant deep learning models being applied to malware detection? Anything like that? Is that a thing yet?
I think that we're so far behind generally in malware detection as an industry that we're not to that point yet. We're still at the phase where when you go through the airport, everybody's showing their sweet marketing picture, how everything's connected, and they don't actually have that running. I think that basic statistical models still provide a ton of data and value when it comes to malware detection, because what we're trying to do is say, here's everything that's very likely good. I can take all the applications in play that are top rated and have more than 1 million installs and have good comments, and I can say, those are probably good, and if they're not good, they're probably so good that I can't, prove it. It's nation state at that point, or maybe they're just amazing. And we're trying to take the stuff that's like just obviously crap and trying to find a way to concentrate on the middle. And there's things that you can do with just like entropy analysis that are real basic that still work great, just like statistical models on maybe what are the, capabilities or, that are available with applications that are associated with things that are malicious. So I don't think we've gotten to the point where we've exhausted the basics yet to even start doing, true deep learning. I hope we do, but I would like to see people exhaust the basics before they start jumping ahead. All right, cool, that's it. Thank you very much.